So up to this point, we now know that we have only really established the existence of a single set, and all that we know about it is that it is inductive, therefore giving us some information about what it contains, yet we do not know everything that it contains, because it may contain more than just the empty set and the empty set plus one, and so on. So our knowledge about what exists up to this point in the development of the axioms is actually very thin. Let's start off by asking whether or not the empty set exists. I claim that it does, and here is why. Whatever that inductive set is, call it X. I will take the subset of X, so let's call it little x in X, the set of all elements of X, such that X is not equal to X. So notice that I am using the separation schema where my phi is u not equal to u, and the parent set is this one set that I now know to exist. Nothing will ever satisfy this formula phi, and therefore nothing is in this set. So I get to talk about this parent set X because of the axiom of infinity. I get to argue that this subset of it, the empty set, exists because of the axiom or the separation schema. So now we have that some inductive set exists. We also have shown that an empty set exists, and we could show that certain other sets exist as well, like the say the singleton of the empty set, which we could get from pairing, or we could just do empty set plus one, which we know comes from unions and so on. So we could argue that the set of the empty set exists one way or another. And so now we know that these things all exist. So now moving on to the next axiom, the final one that we will discuss in this chapter is again not an axiom but an infinite collection of axioms called the replacement schema. And this one says that if f is any function, then for every set x, f of x is our notation for the range of the function, and the axiom tells us that this is a set. So it turns out that this, and of course this is an infinite collection of axioms because every choice of function f determines another axiom, namely that the image of x under f is a set no matter what set x you pick. It turns out that this axiom is in fact strong enough to prove the separation schema. So in fact we could have deleted the separation schema from our list of axioms. We don't, even though that would give us some kind of parsimony, we don't do that just because the separation schema is so natural and sort of fundamental to how we think about sets that we leave it in our list of axioms, even though we could technically get away with replacing it. But there you have it. That is all of the axioms.